Hello. Right. I've already had a few questions just asking, why is this launch so important? Why is it cool? Why does it take 19 hours? Why is the rocket so bloody big? So this is a brief explanation. So this is explaining the SpaceX NASA launch that happened today. Thankfully, went very well, which is great to hear. So the goal is to get these two guys on the Dragon capsule on our wonderful International Space Station. It's quite hard, as you can imagine, and the reason it's so important, and to Americans especially, is it's the first time the Americans have done it since the for like 8 years, okay? So the last time they did it 8 years ago, they've been using the Russians intermediately for the last 8 years to get people to and from the space station. Obviously, people might not be happy about that, but that's the way we've been doing it. So SpaceX says, hey, we can do it, and we can do it cheaper. And that's the key, cheapness. So you have to get a small capsule 400 kilometers up. It's pretty easy. The hard part, 28,000 kilometers an hour that way. Not horizontally, no. Yes, horizontally. So you have to go up a bit, 400 kilometers, nothing really. You can drive that. You have to go 28,000 kilometers an hour horizontally to stay in the air. Getting up there, getting up into space, easy. Staying there, that's the hard part. That's where you need to get the really high velocities required to stay in an orbit. So, if getting up is the easy part, why is stage 1 so big? Why is it so big, right? Does the gravity get less as we go up? No, the gravity is exactly the same. The gravity here is the exact same as the gravity in the International Space Station. The difference is the amount of air resistance. This is why the first stage is so big. So, let's just walk through. Lift off, rockets, go, boom. Go up, right? So we go up, going faster and faster, almost directly upwards, until we start to tilt just a little bit. Start to tilt a little bit because we've got to work on the hardest part, which is our horizontal velocity. So, the scary part, 58 seconds after launch, max Q. Do you know what max Q is? It's the maximum pressure that occurs onto the spacecraft. If something's going to go wrong, it's going to happen there. So, why is it there? Air resistance. It's all about the air resistance. Imagine you're going that fast. Imagine rolling down the window. It'll destroy everything, right? Air resistance is the hardest part. That's why stage 1 is so big compared to stage 2, even though stage 2 gets it going quicker. So, stage 1, loads of air resistance. As soon as it gets 100, 200 kilometers up, the air resistance is massively low. That's why it didn't get any harder on the spacecraft. So, 2 minutes. It's almost horizontal now. Stage 1, that's out of fuel. It's used all that fuel just to get it up and going a bit because of air resistance. So, they turn that off. Chop it off. It's gone, right? 8 years ago, those boosters, solid rocket fuel boosters, that what used to be stage 1, big fuel tank, dump it, disintegrates, falls into the ocean, done. No one cares about that. This is why SpaceX is different and why it's cheap. This stage 1, we can use it again. Do you know how we get it back? It's got to land on its own. Essentially, the rocket has been detached and then it's got to balance somehow. See, I'm even bad at it. You've got to balance it with rockets and get it to land on a tiny platform that's enough for it, just a couple tens of meters wide for it to land on. That's floating in the ocean, right? Land it and be like, hey, cool, we can use that again, just fill it up full of fuel. Great, money saved. Right, that's why stage 1 has a landing thing, and that's really cool. But this rocket, stage 2, is still going. Stage 2 has a vacuum optimized rocket. This rocket is optimized for use in vacuums, e.g. no air, e.g. space. So this second stage is to get it up to that 28,000 kilometers an hour. So that rocket has gone up and it started to tilt just a little bit. Stage 1 drops off about there, and then stage 2 has to take it home. Stage 2 takes about 8 minutes to burn. It's a hard burn, so they're really feeling the G-force in their seats, these two astronauts, and they're getting up to about 400 kilometers up in the sky, and 28,000 kilometers are done. Job done, they've done it. They're in space. Cool. Why have they now got to fly for 19 hours? Why 19 hours going round and round when they could just go and, go to that space station and be happy? Well, the problem is they need to be on the exact same height, speed and direction as the International Space Station. They need to meet it at the lowest differential velocity possible. They can't be hitting into it at all. Things made of paper almost. Slightest thing goes wrong, shreds apart, not great. So they need to meet the ISS at equal velocity. All directions the same, and there's almost standing still next to each other. Why can't they just, point it towards the space station, go, when we stop getting there, just pull it back. That would use so much fuel, it doesn't make any sense. So we do small adjustments in their orbit. The whole reason they launch from Florida is because it's the right latitude, and the reason when it tilts, it tilts in a very specific direction. It's going to get them about 99.9% of the way there. They're almost on the exact same orbit as the ISS, but air resistance, wind, small changes in the rocket. It was a little bit colder than they were expecting in one layer of atmosphere than another. You're going to be slightly off. That's how precise this thing is. So we need to make adjustments in their flight to get it on the exact same orbit as the ISS. So adjusting where you are in space is tricky. Let's say, I'm going to use blue for this. Your rocket is on an orbit around the Earth, and you go, I want to be a bit higher here. Actually, I'm going to be a bit higher on that end. How do I do a rocket up? No, that won't work. That'll use too much fuel. Okay, what do I do? Well, actually, you have to wait till you're here. You've waited all that time. It's tough work being an astronaut waiting. And then you press go. You burn the rocket in the same direction you're facing, going around. You increase your velocity here. Your orbit is going to go up. You're going to go up. And hey! Your orbit is now higher on this section. But wait a minute, you're high on that end and you're still low on that end. Orbits, you want them to be circular. You want them to be exactly the same altitude at all points. So now, hey, you actually have to do another burn here to try and raise your altitude. Here. Well done, you've circularized your orbit. Circularization, that's a thing. So, this 19-hour journey is all about making fine adjustments at little points in your orbit. Tilt it, speed up, slow down, all of these small things. It doesn't require much force. That's why this little Dragon capsule, the one bit that's left, it's got little tiny boosters on it. Doesn't matter they're tiny, you're in space. No air resistance. You can use tiny little rockets, do a bit of a longer burn, a bit of a short burn. You can really control yourself where you are. You've got quite a wide area of how to control yourself. So you get yourself to the same altitude, same orbit as the ISS. Then after 19 hours, 400 meters apart, and you use tiny little burners. You've got the window open at the front, and you just meet them up almost like they're standstill next to each other. Happy days. Consequently, this is how you land it. Hey, I've got hardly any rockets. How do I get back down? You just burn. So let's say you're going that way. You just burn. Pointing that way, and that will lower your orbit enough to go really low to the atmosphere. So you get caught by the air resistance, you get caught by the atmosphere, slows you down, open your parachutes, you land perfectly where you want to be, hopefully, and bish bash bosh, you've landed your aircraft. This has been a short rant about why this rocket launch is so cool and why it's fun and really interesting. Message me any questions if you have any, I'll try to answer them. It's been a few years since I've done space dynamics, but it's still really cool, and do keep up with it. It'll be really interesting to see how SpaceX goes, and interesting to see how Boeing's thing works when that eventually works, I guess. But thank you for listening to my loud, expressive rant. You can see why I tried teaching. Maybe it didn't quite work out, because who knows. Thank you.